So in today's class, we are going to discuss how to use Hough transform to detect circles. This is the agenda for this class. So quickly we'll have the recap of what we discussed for Hough transform in terms of detecting the lines, and then we'll cover this green portion. So we'll discuss how to detect circles using Hough transform, and then as we know that Hough transform is based on voting. So we'll also discuss some practical tips to like do efficient voting, and then we also see how we are handling noise, presence of noise or multiple fragments. I mean, in the Hough transform, and then we'll see there are some challenges, some good things, and some challenges about the Hough transform. So let us quickly see what we discussed in the last class. So to define the Hough transform, we defined actually these two terms, image space and the Hough space. Image space was a space where the input features or input pixels were given in terms of let's say x and y coordinates, and whatever model was fitting through these points, or whatever model on which these points were lying, the parameters of that model in terms of its parameter, it was actually represented in the parameter space. So we see here. So let's say we take the example of line, and if you assume that these 4 points that are there in this image space, there is a line which there is a common line which passes through all these four of them. And if let's say the parameters for that line are m0 and b0, so in the parameter space that is marked here, right? So whatever line we are saying that it is existing in image space, that is denoted by a point in the Hough space. So as we see here, a line in the image space corresponds to a point in the Hough space. Okay. So this whole idea of this discussion is to find out the appropriate values of the parameters of the model for which, if you fit that model, that goes through the selected points or the available feature points in the image space. Okay. So we also saw the example of line fitting, or finding the existence of line in any image using the Hough transform. And in this process, as we discussed in the previous slides, the whole objective is to find out an appropriate model parameters for which the model will actually fit through the points that are given in the image space. Okay. So to find out the appropriate model parameters, we are iteratively processing this, and in place of collectively taking some points from the image space and then finding out what particular model fits there, what we do systematically, we consider the given points in the image space one by one, and then try to find out all the possible values of the model parameters for which we will find a line which goes through, or for which that particular model passes through the particular point. Okay. So let us consider the example of model as lines, as because we have discussed this in the previous class. So if you are saying that we have to fit a line here, or we have to find the existence of line, so then for all given feature points that are here in the image space, for every point we have to consider the point and then find out the possible model values of the model parameters for which you will find a line which passes through this particular point. So if you are just considering one point, we will see that there will be multiple lines which will pass from a particular point, right? So considering one point and then trying to find out the possible values of the model parameters, obviously we are going to get multiple values of the for the model parameters that we have selected. So in the case of line, it turns out that if we have to find out the possible model parameters for which the model or the line will pass through a particular point, that was a kind of plotting a line in the Hough space. So for example, if this strip point is under consideration, so and corresponding to this, we want to find out the possible model values of the model parameters. So then those possible values of the model parameters will be actually falling on a line in the image, in the Hough space. So if let's say corresponding to this particular point, we are saying that this is the line. So then all the values of M and B that are falling below this line, they all are actually the possible parameter values for which if we make a line, that line will pass through this particular point. Okay. So we are doing this for all the points that are given here. So let's say 4 points are given here, and for all those 4 points, we try to find out the possible values of M and B for which the line will pass from them. So if they are, if these all points are falling on one line, then we'll find that in the parameter space there will be one parameter which will be common to all of them, right? Or if let's say we have a few more points, let's say existing like this, which are falling on another line. So we'll see that for all these 4 points which are looking like falling on one line, for them there will be one model parameter for which you will have a line passing from all of them. Similarly, there will be another model parameter common to all these 4. Considering which if you just make a line, that line will pass through all these points. Okay. So basically, the finding the existence of lines is boils down to finding the values of B and M here in the parameter space where you have multiple lines passing from them. All right, or as we discussed in the last class, that when we are plotting a line on the Hough space or the parameter space, from where the line passes, that corresponding value we consider that corresponding value of M and B we consider that gets 1 volt. Okay, so if there is any value of B and M where multiple lines are passing, that means that particular combination of M and B gets more votes. So detection of line actually turns out to detection of such values of B and M where you have more votes, because more votes will correspond to a common line which actually goes through multiple feature points. Okay, so exactly the same criteria we are going to actually apply here in the case of detection of circle in the image. Okay, and all these steps we have discussed in the previous class. We have to iteratively we have to consider each and every point from the feature space, and we have to cast vote corresponding to that point in the parameter space, and then we have to consider the we have to analyze the accumulation of the votes in the parameter space, and then based on the votes, the value of M and B where a lot of votes are being casted, that will actually correspond to a particular line in the model space. If you have only one, this is important to note, if you have only one point in the image in the parameter space where a lot of votes are casted, that shows that there is only one line. But if you have, let's say, 2 points where the multiple votes are casted, that shows that you have 2 lines, and so on. So if you have n places here in the parameter space where the more votes are casted, so we can have conclude that we have n lines in the image space. And please remember, when we are saying lots of votes, this is a very subjective thing. So this depends on what threshold we are taking, right? So depending upon the threshold, we'll decide whether the votes that are being casted for a particular combination of MB are considered sufficient or not. So this again, this will involve thresholding. So now let us discuss the Hough transform for circles. So in case of circle, if you have understood this part, then it will be very easy to understand the concept of circle detection, because the process is going to be exactly the same. So this is a standard equation for the circle where the circle is having center A, B, and it has the radius R. And for simplicity, let's say we are in this particular case, we are trying to detect a circle where the radius is fixed. That means, let's say we know the radius. Okay? We know that in the image, the circle which is existing is of a particular radius. So our radius is fixed. So if the radius is fixed, what are the parameters that are to be decided in this equation? There are only 2 parameters, A and B. These are only to be decided. So in the parameter space, we will have only two parameters, A and B, as you see here. Right? In the previous case, if you remember, when we were finding the existence of line, there the objective was to find out a suitable value of B and M. Now here the objective is to find out the suitable value of A and B, and suitable value means if you choose that center in your image and you make a circle of radius r that is known, then it will pass through the points that are existing there. Right? What we have to do in the previous case, again, if you analyze, we have considered each and every point existing in the image space, and then corresponding to that, whatever the possible model parameter values of model parameters were there, that have been plotted in the images in the Hough space, and whatever model parameter or whatever value of the model parameter that gets the more vote, that was actually deciding the parameters for the circle. Okay, so here let us consider that we are taking this particular point. Okay? So you know if this particular point is there in the image space, and you assume that this particular circle passes from there, this point, then this point will satisfy this equation. So let's say if this the coordinate of this point are xi, yi, xi and yi. So then xi and yi will satisfy this line. So that is why you see that this xi, yi is, when you are keeping xi and yi, left side and right side is same. So now when we are moving to the model, to the Hough space, our xi and y are fixed because you are computing this for this particular point. So they are fixed. Now we have to find out the values of A and B. So they are actually the variable. R is anyway given. So when you are, if you analyze this equation, considering that xi and yi are fixed and A and B are the variables, this basically will is saying equivalent. This is same as saying that you have a circle where the center is xi, yi, and the variables, the two variables with the help of which you are plotting the circle, they are A and B. So basically, the corresponding to this particular point in the Hough space, you will again get a circle. Okay, so you can see here, corresponding to this point, you have a circle here. And what is the center of the circle? This particular circle, center of the circle is xi, yi. So if this point is xi, yi, so then this point, the same point here is there, which has this radius, sorry, the center xi, yi, and all the possible values of A and B, for which if you make a circle, that circle will pass from this particular point here, from xi and yi. Okay? So as in case of line detection for a particular point in the image space, you are getting a line defining all possible values of the model parameters in the Hough space. Exactly here, for a particular point in the image space, you are getting a circle actually defining the possible values of the model parameters, for which if you make a circle, then that circle will pass from that particular point that we have selected, which is here xi and yi, let's say. Okay, this is xi and yi. So we can say that with respect to this xi and yi, when we have plotted this circle, whatever points which are falling below this circle in this Hough space, all of them get 1 vote. Okay. Similarly, corresponding to this point, again, if you just do the same thing, corresponding to this point, again, you will have a circle here, which will define the possible parameters. So all the values of A and B which are falling below this circle, they will actually get 1 vote. Similarly, for the third point, you have another circle. So now when you analyze this voting, then you find that there is one point here where lots of votes have been casted. So that exactly as we said in case of line, here also we can conclude that that particular AB, if you select, then for that AB, whatever circle you are going to make, that circle will pass from all the points which have been considered from the image space in this particular analysis. Okay. So here, this particular point, whatever value you have for this particular point, corresponding to that, whatever AB you have, based on that AB, considering that AB as center and considering the given radius as the radius of the circle, if you plot that, that circle is going to pass from all those points in the image space. Okay. If you have multiple existence of multiple circles, this is we are analyzing just with the help with respect to this one circle that is given here. But let's say you have another circle given here. So with respect to this circle, what are the points you have here? Or I mean, let us assume that there is another circle which passes from these given 4 points. Then corresponding to 4 points, if you analyze, do the analysis, then you will find that there will be another point in the image space where you will have multiple roots, and that will actually define the parameters for this circle. Okay, so I'm just reiterating the whole procedure. Here, when we are detecting the circle, we have to consider all the possible x and y are the feature points that are given in the image space. Corresponding to every point, we have to vote for all the values of the model parameters, for all possible values of the model parameters. And then once the voting has been done for all the points that are there in the image space, then we have to analyze this Hough space. And the model, the values corresponding to the model parameters here, which have more accumulation of the votes, they will actually decide the parameter for the circle. If you have only one circle, then you may have only 1 point here which has more votes. If you have 2 circles, you will have 2 points where you will have more votes. If you have n circles, you will have n points here in the Hough space where you will have more votes. And again, this the votes are more or less, that will be again decided based on a threshold. Okay. So as I just said, so based on the accumulation of this accumulation of the votes at this particular point, we decide the we decide the center for this circle here. Okay. So this was the case when radius was fixed. Okay, and one more thing I have written here is a gradient direction. Gradient direction, that means if we are assuming that the points that we are considering the image space, they are the edge points. So when we have detected the edges, we must have computed the gradient and gradient direction. So if that is known, we can make use of it. If it is not known, then obviously we have to do the more computation. So in this particular case, we are assuming that radius is known, but gradient direction is not known. That means the coordinate points of the those pixels, those feature points, or those S pixels, coordinates are known, but their gradient is not known. Later we will see that when the gradient is known, our computation will further simplify. Okay. So in this particular case, now we have unknown radius. In the previous case, the radius was fixed. Right? See this, the radius is fixed, gradient is unknown. Now here we have the radius also unknown and the gradient is also unknown. Okay. So here our computation becomes more, because now we have to look for all possible radius values. Okay. So now how many parameters we will have in the Hough space? We will have 3 parameters, because along with A and B, now R is also a variable. So we don't know that what size of circle is present in the image. Okay. So now here, for any given point, let's say this xi, yi, we have to consider all the possible values of A and B, and also for R. So for simplicity, we can assume that R has initially, let's say, 0 value, then R is increased to 1, then R is increased to 2 and 3 and so on. So incrementally we increase the value of R, and that for that particular value of R, we search the image space. Okay. So if you do that, corresponding to a particular point here and for a given radius, you will have a circle. But if this circle will change its size and shape when the radius is reducing or radius is increasing. So for a particular radius, if in this Hough space, if you have, let's say, you have plotted a circle like this, then when you increase the radius, this circle will become like this, right? Or if you reduce the radius, this circle will become like this. So in the Hough space, when you are plotting the all possible parameter values by considering A, B, and R as variable, this collectively will actually look like a cone. So it will be like a cone. For a particular xy that you consider from here, this plot for possible values of A, B, and R, this will look like a cone. Okay, and surface of the cone will decide actually the parameter. So if you choose any point on the surface of this cone, that will decide appropriate A, B, and R, and based on that we can define the circle. Okay, so if you have the multiple values, multiple points here, for every point you will find that there will be a cone here. So if you consider more points, let's say one more point, then you have another cone, and like that. So when you consider multiple points from here and then cast the vote here, in this case now we have to look for the accumulation of the votes in 3D, three-dimensional space. So initially it was a 2D grid, but now in this case it's a kind of 3D grid where a particular cell will have 3 coordinates. The location of a particular cell will be decided based on A, B, and R. So a particular cell where a particular cell for A, B, and R, which has got more number of votes, that will actually decide the model parameters. So given these points, we just go here to plot these cones, and then after plotting the cones, we'll analyze that 3-dimensional grid, and then the cell which has more accumulation of votes corresponding to that, whatever A, B, and R we have, that will declare the parameters for the circle or parameters for the existing circle in the image space. Okay. Now let us consider the next case where radius is unknown, but we know the gradient direction. Right? So for every given point in the space, in the image space, we know what was the gradient direction. Okay. So based on that actually gradient direction, we can find out the location of this circle, location of the center of the circle. One more thing you notice, you can again notice from this equation, what are the parameters we are going to trying to find out? That's A and B and R. And what is A and B? A and B is the center. So if we know the gradient direction at a particular point, then actually we know in which direction the center will lie. Then we don't need to search actually all around. In the previous case, we have to search for all possible values around x and yi, xi and yi, for which we will have a circle. But in this case, to search a center, if we are saying that this is a particular point here and the gradient direction is this, so then our center will also actually exist in this line only, right? So that is why you see that the center is existing here in this case. Okay. So here now the things are a bit simplified. So when we are plotting basically the possible values of A, B, and R for a given point, now this is no more a conical shape. This is kind of line, because if you just if you analyze that conical shape in pieces, then this conical shape was actually coming, or this was actually the collection of multiple circles that we have got for different radius values. And for a particular circle, you see that the periphery of the circle, the circumference of the circle was actually telling the possible values of A and B. Now here that is known. We have only one direction in which we have to search for the A and B. Okay, so that is why this is no more a cone. This is like a from every circle actually we are getting 1 point. So if you just join those points, this is actually going to form a line. So in this case, voting is being casted in 3-dimensional space. You are going to get a 3D grid, but it is not going to be as complicated as it was in the previous case where the votes were actually casted by choosing the points on this, on the surface of the cone. Right here, it is just line. Okay. So let us summarize the algorithm for detecting the circles in the Hough space. It's a circle in the image space using the Hough transform, and for this we are assuming that our coordinate system is like this, as we explained here. X-axis is this side, y-axis is this side. So we know that if x-axis and y-axis is defined like this, and you have a point on the circle, its value can be defined parametrically as x equal to a plus r cos theta and y equal to b plus r sin theta. And since now we are going to compute a and b here, so there is very a and b are on the left side, and x and y are on the right side. Okay, so this is actually the parametric equation of the. We are to get these equations, we are using the parametric equation of the circle. Okay, so how does the algorithm proceed? We see we are going to iterate for every edge pixel present in the image. So we are considering a particular xy, and for each possible radius value r, and for each possible gradient direction theta, we are going to compute the value of a and b. And for that particular a and b, and whatever the radius we have chosen from here, corresponding to that in your three-dimensional grid H, if a vote is being implemented. Okay, so for every xy, we are going to do this process, and in the three-dimensional grid H, the votes are going to be added, and at the end, when all the H pixels have been considered, and for every pixel, all the possible values of radius and all the possible values of gradient have been considered, then whatever outcome we are getting in H, that need to be analyzed to find out the cells where the more votes have been casted, and based on that, we need to declare the parameters, model parameters for the circle which is existing in the image space. Okay. So if in this case, if we are for a pixel xy, if we know the theta, if we know the gradient, then this theta is going to be a one value, and corresponding to that one value only we have to compute the values of this a and b. Okay. Now let's see a few examples. So let's say this is the image given, and we have to find out the existence of circles in this image. Now you can notice here that we have two types of circles here. One is a small circle, this is called quarter here, a penny here, and then another is a quarter, right? So we have to detect these circles, and let us say that if you know the value of the radius for these points, then we can perform the Hough transform, let's say 2 times for those 2 fixed radii, and then we can find out the parameters for the circles that will fit to these points. Okay, so this is the step. In the original image, we have to first perform the edge detection to find out these feature points are the edge points. Okay, and on these considering these edge points, we have to go to the Hough space, and we have to vote for the possible values of the model parameters. So now in this particular case, we are, let's say, detecting the penny, right, the smaller coin. So when we are saying that we are voting for the penny, or we are detecting the penny, this basically means that we know the radius of this penny, and for that particular fixed radius only this whole exercise is being performed. So that is why you see that this particular point here gets more votes, which is actually the center of this penny, because for that particular radius you have only one circle that is existing here in this image here. Okay. At rest of the places you see some votes, but the intensity of the vote, intensity of the dot that you see here is much more compared to the other places. So based on the value that you have in the Hough space for the possible values of the model parameters, we can decide the appropriate model parameter. Now please remember here, this space is in the Hough space, whatever you are plotting here, it is a 2D space. That means, and why it is a 2D space? Because this is like the first case that we discussed, where the radius was fixed. The radius was fixed, so the parameters were only a and b. So you can say that this is a here, and this side is b here, right? So only we are trying to find out the suitable values of a and b because we know the r. So based on when you are moving from here to here, whatever the voting you have got in this space, then you have to threshold that to find out the point where the enough number of votes are there, and then corresponding to that point, you will get a and B, and that A and B can define the circle in the image space. Okay. In this case, we are actually trying to detect the quarter. That means the radius that we have supplied here while performing the Hough transform is the radius of these bigger circles, bigger points. So that is why you see the dots, the bright spots are actually coming at these 3 points here in the Hough space. And corresponding to them, whatever A and B we are getting, that will define the circles in the image space. So again, here this is A, and this side is B, and a particular A and B, let's say you are choosing this AB, this will define the circle, center of the circle, and our radius already we know, so based on that we can go to image space and plot the circle. Okay. Now let us see some practical tips that we need to consider when we are going for this kind of processing. So to minimize the irrelevant tokens, or to actually minimize the effect of the irrelevant feature points from the image space, we can actually consider the gradient magnitude before considering a particular point. So for example, if you just go here, in this image, you very easily you can actually see that whatever gradient magnitude you will have for these boundary points here on the circle on the edge of this coin, the same amount of change you will not see, change in the gradient you will not see on the points, for example, which are here, right? And you know very clearly that these points are not of our interest. They are the, in some sense you can say they are the noisy points, and they don't need to be given much importance. So which point is important when you do the edge detection and get these points, to find out which point is more important, which point is less important, we can actually consider their gradient. Wherever the gradient is more, we can say that that point is important. Otherwise, we can say that the point is not important, and then it should not be considered for the voting. Or if let's say it is considered for the voting, then its vote will have less value, right? Another example actually you can see here. So for example, there is a tail kind of thing here, but in the image here, you don't see a true tail like this. So these points that you have here in terms of h-axis, those points are not the true points. And if you just analyze their gradient, you will find that they will have a very weak gradient. So just by using the magnitude of the gradient, actually you can find out what are the reliable points in the feature space or in the image space, and based on them only you can cast the vote. So either there's one option that you can completely overlook those points. Second, maybe you can just weight their vote based on the proportional to their gradient. Okay. Now there's another parameter which is very important. It is the grid resolution. So in every case, you see that whenever we are in the feature space, in the Hough space, and let us consider this space where we have just two variables A and B while detecting the circle. So in A and B, there is one option that every possible value of A in this side and B in this side is considered as one grid cell, right? Every intersection, like for a particular A here and for a particular B here, whatever this intersection is coming here, that is considered a particular AB. Okay, but in that case, this is one option where we say that actually the grid is too fine. Okay, now in this particular case, if your grid is very strictly defined, then you will see that, let us say you have a particular AB here at this intersection, it is getting some votes. Okay, and there is a very close to this AB, there is another point, another AB, which is also going to get more votes. Now this these both the ABs that you see here and that you see here, they both might be actually belonging to the same circle, but in the parameter space, this AB has got little deviated because the point that we considered on in the image space, they will not perfectly on the circle. There might be some deviation. If all the points, if there is a circle in the image space and all the points that we have detected, they are perfectly on a particular circle, then obviously all the points that we are considering from here, they will cast vote to a particular AB. Okay, but if there is a little deviation in these points, let's say this particular point, when you did edge detection, this was not exactly at this place. Let's say got little deviated to this point. Similarly, let's say this point got little deviated to this point. So because of that, for these points, let us say, I mean, in this example that we have, let's say 10 points. Out of those 10 points, there are 6 points, let's say, which are falling perfectly on the circle, on one circle, but there are 4 points because of the noise or because of some other reason they got deviated. So corresponding to those 4 points, whatever AB you are getting, that will not be the AB here, they will be little deviated AB. But you know that they all belong to the same circle. So if your grid is very fine, then you will find that one circle will be declared based on this AB, and then another circle will be declared based on this AB. But if you make your grid little sparse, and let's say you consider that all the points which are falling in this particular range are in this particular range of AB, and in this particular range of in this particular range of A, and in this particular range of B, if they all actually vote for a same AB, then you'll find that these points will be considered common. These points will be considered voting for the common AB. Okay, so that way you'll see that you will be able to detect the correct circle. Otherwise, if your grid is very fine, then you will detect 2 circles for the same these 10 points that are given here. Okay, so there is a problem if you make the grid too fine, then you will see that a lot of circles, a lot of models will be detected, which may not be, all of them might not be the true model. Maybe multiple models may correspond to the same model in the image space. So the grid should not be too fine, but at the same time, grid should not be too coarse also, because if you make a too coarse grid, that means if you, let's say, in place of saying that this particular cell is made by using the A and B in this range, if you, let's say, expand this, so if you make this particular grid, let's say, more wide, and then say that up till this point we are going to consider the points in the same grid, then let us say you have expanded this to this point, and this B is expanded to this point, right? I'm just little making it thick so that you can understand. So now our grid is one grid cell is I'm sorry. So this is basically the line, this line, and this line. Okay. So the one grid is basically consisting of all the ABs that are falling here in this bigger square. So when your grid is big, you will actually consider this particular AB and this particular AB same. Where in reality you see that those AB have much difference. Okay. So our grid size should not be, or the discretization that we are using to define the grid, that should not be too fine, because otherwise you will detect a lot of models. And if it is at the same time, if it is too coarse, then you will actually lose out the many models existing in the image. So that's why we have to actually suitably choose the size of the grid. Okay, and sometimes to actually nullify the effect of noisy pixels and all, after getting the votes in the Hough space, we do smoothing, and then after smoothing, whatever we get, that is actually considered for computation of the suitable suitable values of the model parameters. Okay. And as we have seen already, we can utilize the direction of the edge to reduce the free parameter by 1. So if you are using the direction, in the case of image also we have seen, in the case of edge also we have seen, and in the case of circle also we have seen, the number of parameters get reduced. Right? The number of free parameters that we need to search, they get reduced. Okay. And one more important thing we need to keep in mind is this. Whenever we are detecting a parameter, suitable value for a model parameter, we have to go back to the image space and we have to plot. Okay. So when we are going and plotting that, we also actually need to keep track of those points of the image space which voted for a particular parameter value in the Hough space, so that when we are going back, we know that if this, let's say this is a particular AB for which we are going to plot the circle, then what were the points corresponding to which you are getting this circle. Right? So to have the reverse mapping, when you are casting the vote for a particular vote, you need to store what was the point who has actually voted for it. Okay, so that way when you are selecting a model parameter, selecting a value of model parameter in the image space, in the Hough space, so corresponding to that, when you are going to plot the model in the image space, you know that what are the corresponding points that need to be included there. Okay. Fine. Now let us see how are we able to handle the presence of noise when we are doing the Hough, when we are performing the Hough transform. So in case of so let's say this is a very ideal case where there is a line here. Now because of the noise, let us say, and when there is a very clear-cut line here, you see that there is only one peak. But let's say if you have because of the noise, there are some pixels here on the edge which have got deviated. Let's say this has gone here, this has gone here, this has gone here. But as we know that decision of existence of a line in this particular image, let's say this line, is not just based on only these 3 points, right? It is based on many more points. So since we are considering a lot of points to take the decision, even if the few points are noisy, that doesn't make any difference in this case. Okay. You can compare this with the case when we do line fitting. This is, in this case, please remember that we are not doing line fitting. In the line fitting, we consider some set of X and Y, and then based on that, we decide appropriate line. Here, we are not doing that. Here, in the Hough space, I mean, the value of the parameter which gets more votes, based on that only we are deciding the parameters for the line. Okay. So in this case, suppose we consider that there are 100 points on the line, and then out of that 100 points, 10 are noisy. So they will actually not vote for the correct parameter value. They will vote for some different parameter value. But since we are going to decide the existence of line or the parameter for the line here based on the majority, so even though in your, let's say, parameter space, because of the 90 correct points here, you have they all have voted for this particular, let's say, M and B, and those noisy points have voted for this. So you are going to take decision based on only this value, not based on this value, because they are not in majority. That value is less. So if you choose this B and M, you will see that it's still, since though some points were noisy, but it's still the line that will fit in these points, that will be the correct line. So that way we are able to handle the noise there. And similarly, multiple fragments also doesn't make any difference here, because even though we have some missing points, but with the help of these points and these points, we can find out the existence of the appropriate line. So this is, in some sense, we can say that when we are detecting the models with the help of Hough transform, we can actually handle the occlusion. So if some part of the model is occluded, even though we will be able to detect the the model. For example, in this case where we were talking about coin, let us say in this coin, some part of the coin is hidden. Let's say this much part is not available, but it's still based on this part and this part, we'll be able to detect this circle. So this can here we can handle the multiple fragments, or in other way we can say that we can also handle the occlusion. Okay. Now let us just briefly discuss what are the positive points and what are the challenges in Hough transform. As we discussed, Hough transform can actually cope up with the occlusion. So if your model, existing model in the image space has some occlusion, so still we are able to detect that model. So that's a good thing. And it is robust to noise, as we just discussed. And it can also detect multiple instances. If you have in your image space, if you have one line, that will be detected. If you have two lines, that will be also detected. If you have n lines, that will be also detected. So it doesn't matter how many instances you have, all the instances will be detected. What are the problems? So there are some challenges actually when you are implementing the Hough transform. Its complexity actually increases. It is exponentially increases in terms of the model parameters. So the complexity of the process is actually high, and it is increases as the model parameters increases. And then second is the quantization. We discussed that we need to select a good grid size, but it's quite challenging to find out suitable grid size which will give the correct detection. Right? So this is another challenge. So with this, let us conclude the discussion on Hough transform.